This tutorial will walk you through the basic steps needed to create a dense surface point mesh. There are 4 basic steps to create a point mesh. Set up the project and process to orient the cameras. Run the dense stereo DSM routine to create a point cloud mesh. Optionally use the Modify Mesh tool to triangulate, decimate, or smooth the point cloud mesh. We start a new standard project. Select your images. They are automatically matched with a camera from our calibration library. Here are 3 photos of a footprint. Strips of coded targets have been placed around it to help orient the cameras. See the automatic targeted project tutorial for more information on coded targets. You do not need to use targets. You can also orient your photos using manual mark and referencing or using Smart Match. See the Smart Match Point Mesh DSM walkthrough tutorial for more information. We could have set the project up using the automatic project wizard, but this tutorial will walk through each step, showing how to run them manually. First, we will use the auto marking tool to detect the coded targets. Then we will process the project and verify we are getting a good result by checking the largest residual and camera positions. Contrary to non-point mesh projects, dense surface projects require low-angle stereo-like photos for DSM processing. Here, photo 1 and 2 provide a good low-angle stereo pair. To give redundancy and help strengthen the orientation, a third, higher-angle photo has also been included. This photo will not be used in the point mesh generation. It is only used for this orientation step. Another requirement for creating dense surface point meshes is the subject matter should have a random pattern or texture. In this case, the sand has both. Unless you recreate them, once a point mesh has been created, it is not advisable to reprocess a project since the point meshes will not be affected by any changes done during processing. To make the units displayed on the dense surface dialog match the real world, we need to set a scale. The distance between these 2 points is 161 millimeters. You can define the area used to generate a point mesh in 3 ways: by drawing a 2D trim on one or more of the photos, by defining and selecting a surface, or using the whole photo extents. In this case, we will add a DSM trim to surround the area we are interested in. We open the Create Dense Surface dialog. The information at the top gives an indication of the project's quality and if it is suitable for generating a point mesh. Your project must be solving well and have low residuals. The trims and surface information defines what extents and approximate starting point the dense surface algorithm will use. The base to height ratio shows the minimum and maximum base to height ratio for all selected photo pairs. Ideally, projects should have a base to height ratio between 0.1 and 0.6. This next section shows which set of photo pairs should be processed. We'll use a stereo pair, photos 1 and 2. The settings section shows what values will be used during point mesh creation. When you select an item, the description for the parameter is displayed below. You can increase or decrease the size of this window. For sampling rate and depth range, there are also hyperlinks to have a default value recalculated. Sampling interval controls approximately how much space is between each point in the point mesh. In this case, Photomotor will try to scan a point every 2.55 millimeters. The larger this number, the faster the point mesh will be created, but also the sparser the point cloud will be. Extents from controls what area of an image will be used when creating the point mesh. In this case, we can choose between the DSM trim region we defined or the whole photo. If we had added a surface and selected it, we would also have the choice of defining the extents as coming from the surface's area. The depth range controls how far above and below the approximate surface the point mesh algorithm will search. When you have a surface selected, the height specified is the distance above and below your surface. In this case, we have no surface selected, so an implicit surface will be created using the points in the project. As our points are mostly in one plane, the implicit surface created will be along that plane, which is a reasonable approximate surface for this footprint. If you decrease the depth range, less data will be processed, so it can speed up the point mesh creation. It also limits the search area, so it reduces the chance of an incorrect point location being identified. However, if the depth range is too small and the valid location lies outside the search range, it can never be found, and as a result, there's a good chance an incorrect location will be matched, resulting in noise. The troubleshooting tutorial shows an example of this. The advanced parameters can usually be left at their defaults, but the troubleshooting tutorial shows some cases where you may want to adjust them. The matching region radius defines how large the search area window is. With a radius of 5, a region of 11 by 11 pixels will be used when comparing data between the two images. Depending on how random the pattern on your object is, you may need to increase this number if points are dropped out. The larger the window, the slower the processing will be, as it needs to compare more pixel data. Texture type controls how strong a match needs to be before it is thrown out. If your point mesh has little or no noise, but lots of drop points, lowering this number may help. If you find excessive noise in your project, increasing this number may drop more of the noise points. Downsample factor controls the resolution the scan is done at. Leaving it at 0 will automatically calculate a reasonable size. The isolated point filter will remove any clusters of outlier points. Subpixel controls whether the matching is done on an integer pixel basis or, for more accuracy, at a floating point less than 1 pixel basis. Supersampling controls how the subpixel sampling works. If you find ripples or waves in the data, increasing this value may help reduce it. The meshing options on this tab are briefly covered later in the tutorial, and covered in more detail in the modified point mesh tutorial. Before meshing, you will need to generate a good point cloud, so they will be off by default. To start with, it is a good idea to leave the default parameters and create a point mesh to see what the output is like. You can then adjust them to optimize the output to your liking. We hit execute to create our first point mesh. A mesh with 3,331 points is created. We open a 3D view to look at the mesh. You can see how the mesh matches the data in the photo and extracts the depth of each point. From this view, you can see there are holes in the mesh. This is because these areas are not visible on both photos. If you view the mesh from a similar angle as the photos were taken, you can see how all areas visible are accounted for. If we had taken the images from this angle, it would have included data in the gaps, but we would have other gaps on the far side. Images taken directly above may provide data for all areas for this particular shape, but another technique is to include more than one set of stereo photos. If your end goal is a triangulated mesh, holes like these can be filled during triangulation, as covered later in the tutorial. We will create a second point mesh, this time lowering the sampling interval to 1 mm to increase the number of points in the final mesh. This mesh has 21,745 points. We can turn on textures to see the point cloud colored using data from the photos. Here is the colored point mesh. You can zoom in to see the point density. Now we select a mesh and choose the Modify Mesh command. Using the default settings, we will produce a triangulated point mesh. More information on modifying the mesh